Number 8, we're being asked to find both the local and absolute extrema of the function g of x equals 3x minus 4 over x squared plus 1 on the closed interval negative 2 to 2. So the first thing we want to state is the domain of the function, because any number that's not in the domain is not eligible to be the location of a local or absolute extrema. All right, so the only domain potential problem we would have here is when x squared plus 1 is equal to 1. Or is equal to 0. But if you were to subtract the 1 over to the other side and take the square root, you get imaginary solutions. So the denominator doesn't have any real solutions, which means that the domain is all real numbers. All potential critical numbers that we find are in the domain. Okay, so now we're going to need the derivative, because that's how we find our critical numbers. So this is going to be a quotient rule. Low d high less high d low over denominator squared. So let's clean up the numerator just a little bit. Distributing the 3, we're going to get 3x squared plus 3. And then let's distribute the negative and the 2x into the other set of parentheses. So we're going to get a minus 6x squared plus 3 times 4 is 12 times 2. Oh, no, sorry, just 2 times 4, plus 8x. All right, so adding together our like terms, our derivative is equal to negative 3x squared plus 8x plus 3 over x squared plus 1 squared. All right, critical numbers occur when the derivative is equal to 0, which is when the numerator is 0, and when the denominator is 0, which is when the derivative does not exist. Now, we've already talked about how the denominator never equals 0, not for any real solutions. So the derivative exists everywhere. All right, in the numerator, solving that guy, let's see, if you factor out a negative sign, then you've got 3x squared minus 8x minus 3 equals 0, which actually does factor nicely. Make sure, hopefully not too low on the screen here. This factors as 3x plus 1 times x minus 3. So our two critical numbers are negative 1/3 and 3. Now, keeping in mind, we're only interested in the local and absolute extrema on the closed interval negative 2 to 2. 3 is not in that interval. So negative 1/3 is our only critical number in that interval. The only potential locations for absolute maxes and mins are at the critical numbers and the endpoints. So we go back to the original function and we plug in the endpoints, g of negative 2 and g of 2, and we plug in the critical numbers. Number g of negative 1/3, sorry. G of negative 2 is negative 2. G of 2 is 2/5, and g of negative 1/3 gives us negative 9/2. As far as absolute maxes and mins go, we're guaranteed that we're going to have an absolute max and min on this interval because we're continuous on a closed interval. So by the extreme value theorem, it has to have an absolute max and min. So the lowest of these is the absolute min. Negative 9/2 is what? Negative 4.5. So this is our absolute min. And then the largest of the numbers is our absolute max. So that's going to be 2/5. Local maxes and mins can only occur at critical numbers, not at endpoints. So since this is our only critical number, this absolute min is also a local min. But since the absolute max is at an endpoint, our conclusion is that there is no local max. So absolute max of 2/5, absolute min of negative 9/2, local min is also at the absolute minimum point, and then there is no local maximum.